Hi everyone, Dr. P here, and in this lecture video we'll go ahead and take a look at an overview of the modern model of the atom. Now we'll be getting into a lot more detail about the modern view of the atom, modern atomic theory, later on in this semester, but for right now this video will be sort of a little overview and also a little introduction to the periodic table. So what is our modern view of atomic structure? Okay, well, as Rutherford found, we have a concentration of mass and positive charge in a tiny bit in the center of the atom called the nucleus. So we have a tiny nucleus, something around 10 to the minus 15th meters, which is, let's see, 10 to the minus 9 is nano, 10 to the minus 12 is pico, 10 to the minus 15 femtometers. So the tiny nucleus, and that's comprised of protons and neutrons. And so this is relatively massive. And then we have some kind of cloud of electrons. And these are around 10 to the minus 10 meters from the nucleus. So the nucleus would be at the center of a little cloud of electrons that's about 10 to the minus 10 meters in radius. And these have relatively little mass. So for example, the mass of one electron is roughly 1/1000th mass of a proton or mass of a neutron. About 1,000th. It might be more like 1/2000th, but anyway, you get the idea. It's really, really small. Now, the properties of our properties of our atoms, rather, are going to derive from the number and arrangement of electrons. I'm going to abbreviate electron as E minus. Now I should note that these are chemical properties. There are some properties such as density, which could depend on number of neutrons. But we'll talk a little bit more about that later. So for neutral atoms, our number of electrons equals our number of protons. I'll just abbreviate that proton as P plus, always. If we have fewer electrons than protons, then we have a positively charged ion. If we have more electrons than protons, we have a negatively charged ion. Or ions, charged particle. So our number of neutrons can vary. I'm going to abbreviate neutron as N0 because there's no charge. So for example, we could have carbon 12, we could have carbon 13, and we could have carbon 14. And all of these have 6 protons and 6 electrons, but we'll have 6 neutrons. Oops, sorry about that. 6 and 0, or 7 neutrons, or 8 neutrons. And so species that have the same number of protons but different numbers of neutrons are called isotopes. All right. So let's take a look then at some ways that we go about just representing atoms and elements when we talk about them in chemistry. Now notice I described what things look like, but I didn't draw a picture. We'll draw a picture later on in the semester. We'll start looking at a little more detail. Right now we're going to use this kind of symbolism. So I'll talk about that in just, actually maybe I'll talk about it right now. So let's say we had some atom X, and then in this atom X we have some numbers here. We have, let's do, how did I want to label these? I don't want to get confused later on, and I don't have my notes for the later chapter. Well, this is our atomic symbol. We can have our, let's just call it here, N. This is our atomic number. And then we can have Z, which is our mass number. And then we will have over here, we will have Q, which is our charge. And if Q is 0, we don't bother to show it. So an example of this could be carbon 12, where our symbol is C for carbon. Our atomic number is 6. And really the atomic number written out with a atomic symbol like this is kind of from the Department of Redundancy department, because, well, only carbon has an atomic number of 6, but only carbon has an atomic symbol of C. So the two just kind of go together, and you don't necessarily need to have that guy right there. So often we don't bother writing that. 12 is our mass number, and the mass number is equal to the number of protons plus the number of neutrons. And in this case, for example, we have no charge, so I could put a little 0 there. And our charge is equal to the number of protons minus the number of electrons. So if we have more electrons than protons, we have a negative charge. Example of that could be sodium plus, or sodium 1 plus, where we have one extra electron, one less electron than we would normally have. Sodium is also has a 23, Wayne, 23, and 11, sodium 23. All right. Now, we can see a little bit more of this representation in the periodic table. And the basic idea here, you can see it here, is that we have the elements arranged in this table format such that we have vertical columns called groups and vertical rows called periods. Sorry, horizontal rows called periods. And the vertical columns or groups have similar chemical properties. So we'll say elements in columns or groups have similar chemical properties. And then the horizontal rows we called periods, and then we have metals versus nonmetals. Metals tend to lose electrons to form cations. Of course, cations are positively charged ions. And nonmetals tend to gain electrons. We'll look at this in just a little bit. And they form anions, which are negatively charged ions. And nonmetals will also bond with each other in some other ways, and we'll talk about bonding in just a minute. So we can take a look here, and this region that's kind of in the sort of yellowish beigeish color, those are metals. The green-gray here are nonmetals, and sort of the light pink mauve here are what we call these semi-metals or metalloids. And they have some properties of both metals and nonmetals depending. Most metals are conductors. They tend to be shiny. They look metallic. Nonmetals tend not to be shiny. And you'll have things that are gases. None of the metals are gases at room temperature, but things like nitrogen, oxygen, etc. are gases at room temperature. Those are among the nonmetals. And we'll look in just a minute at how atoms combine to form compounds. Some other things to note here in the periodic table, we have our group numbers. Notice they're 1 through 18, and these are what I call the new school group numbers. They're the IUPAC group numbers. There were some older ones, which are often shown as Roman numerals, and I call those the old school group numbers. And they dated back from an earlier time in the periodic table. If I get a chance, I'll show you one of those periodic tables. I don't have one right now. But those old school group numbers were actually useful for some, for determining some things about how your different elements in a given group might react, and we'll talk about that in just in a little bit. So what else can we say here? Well, the position of an element in the periodic table is going to determine how it tends to react. So hydrogen here has 1 proton and 1 electron. Helium has 2 protons. Also, helium-4 at least has 2 neutrons and then 2 electrons, etc., etc. So let's, for example, look at sodium. Sodium has 11 protons and 11 electrons. It's a metal, so it will tend to lose an electron and form a sodium ion. Magnesium actually tends to lose 2 electrons to give us Mg2+ ion. Notice its location. So it will tend to lose 1, 2 electrons, and it will basically we'll be counting over, and it will sort of have a similar configuration to neon. And again, we'll get into the details of electron configuration in a later chapter. But the metals tend to lose electrons, and the nonmetals tend to gain them. So like oxygen will tend to gain 1, 2 electrons, so that it lines up with the, matches up with a noble gas. So basically, electronically, the number of electrons equals the number of electrons on neon. Because oxygen normally has 8. If it gained 2, it would be an O2- ion, and it would have the same number of electrons as our noble gas, neon. These noble gases are called noble because they tend not to react with things. They're rather unreactive. All right, let's see what else I want to say about the periodic table now. I think that's about it for now. We do have this little key here showing atomic number, the symbol. Again, the number and the symbol kind of tell you the same thing. Atomic mass, that's different than our mass number. Mass number is number of protons plus number of neutrons. Atomic mass is actually a weighted average of all the different isotopes. So we have hydrogen. Well, let's look at carbon here. Carbon with a mass of 12.01. That's the atomic mass. Well, we didn't have any carbons that have a mass of 12.01. We have carbon 12, carbon 13, carbon 14, because the mass of a proton is about equal to the mass of a neutron. So instead what we have is on planet Earth we have some ratio of these different isotopes, and if we took an average of those, that average sample would have a mass of 12.01 grams per, in this case it's a mole, and we'll talk about moles in chapter 3. But anyway, just to give you an idea of what those mass numbers are, or sorry, what the atomic masses are all about. Okay, now one last thing that I just wanted to talk about before talking about nomenclature, which will be the next video, is I do want to just briefly talk about molecules and ions, because the next videos will be looking at naming molecules and ions and compounds. Okay, so atoms will bond together via chemical bonds. And these are forces that hold atoms together in compounds. We have different types of chemical bonds. We have covalent bonds, where atoms share electrons. And then we have ionic bonds, where atoms gain or lose electrons to form ions. And then we have an electrostatic interaction between oppositely charged ions. So we'll say atoms gain / lose electrons to form ions oppositely charged ions attract. And there's a few different ways that we can represent our molecules. We can do a chemical formula. So for example, CH4 is the formula for methane. We could do some kind of structural formula. Where we show how our hydrogens and our carbon are attached to each other. And these kind of funky wedge and dash symbols here refer to 3 dimensions. So this is has a 3-dimensional shape. We can also make models. These include things like space filling models and ball and stick models. Not ball and stick, ball and stick. And later on, we will have an opportunity to make some ball and stick models ourselves with molecular model kits. And that'll be later on in this semester. All right, so that's an overview of our view of the atom and also an introduction to the periodic table. We'll take a look at how we name things in the upcoming lectures. So until then, stay safe out there. Bye now.